hope it's showing. Hello, everyone. Let's see if it's showing here. Yes, it's working. Hello, everyone. I hope that you all can hear my audio. If you cannot, please send some comments here in the chat. I appreciate that. And welcome you all. We have again one more webinar organized by the Brazilian Tunneling Committee in English. So we can have some international attendance as well, some participants. And we are receiving again Marco Mulada. Unfortunately, Michael cannot come this time. He will attend the next one. It's a very nice topic. Before I go to the topic, I would like to remind you all to please follow our channel if you haven't done so. And also, questions are most welcome throughout the presentation. I will keep track of it. So I'm going to pass now to introduce Mark. So Mark has been working at MTC for over 18 years. He graduated in civil engineer at the Polytechnic University of Catalonia in Barcelona. Mark is company procurator and head for international projects and has participated in all tunneling project stages, from initial feasibility studies, bid preparation to detailed design and construction of large TBM tunneling projects. He possesses a wide hands-on experience in tunneling, having assisted several job sites worldwide, covering all existing TBM technologies in a wide variety of ground conditions. About the MTC, the invited company for this webinar, MTC counts among the world's leading experts in TBM tunneling, providing design and consultants services to owners and contractors. They have a very close and familiar relationship with Brazil, where they have been providing service to the largest Brazilian contractors since 2002, as some examples citing São Paulo Metro Lines 4, 5, and 6, as well as Rio de Janeiro Line 4. So I welcome Mark.
Yes.
Welcome.
Hello.
And welcome again. And then I'm going to share your screen now.
Good. So, well, thank you very much, Daniela, again, for the introduction. Again, I'm very pleased to participate in this webinar hosted by CBT. The third webinar, actually, we're holding now on different topics of TBM tunneling. And today we have a topic which maybe is one of my favorites right now. It's quite a difficult topic and also quite an important topic. And this you can see on the screen, it's on predicting the tool wear in soils and planning the cutter head intervention strategy. So this is a short overview of the contents we'll go through today. Well, I'll start with an introduction, then we'll discuss the tool wear. Inside the tool wear, we have, we'll go through the governing factors, the factors that govern the tool wear, how actually abrasion is measured in soils, then how we are correlating abrasion and wear, and how we do the management of the tool wear. And then finally, then we continue with interventions and aspects like when to intervene, types of interventions, procedures for interventions, and then finally a strategy approach to handle this topic, and some concluding remarks. So just a very brief introduction. I mean, this is going to be quite a presentation with quite a practical point of view, among other reasons, because for tool wear prediction and intervention planning in soils, it's a very, very important topic for designers and contractors, but there's hardly any solid theoretical models or background. Yeah, because it's as we'll see today, and that's, I think, the main aim of my presentation, to show that it's very complex, all the variables that it involves, and different than in rock. In rock, we would be able here to present, if we were handling this topic with rock, to present different existing models which are more or less validated and more or less complex, but actually there's no real soil or toolware prediction model in soils. So it's all based very much, as I point out in the second bullet point, on the experience very much of designers and contractors. Okay, and while it is although it is a very important aspect, because it is a main cost and time driver in shield tunneling projects in soils, and it is very often a source of losses and disputes. So starting with the governing factors, we will start with abrasion, which is what I think most people come up with when they think of wear, but it's not only about abrasion, and we'll keep on seeing this right now. So the important aspect of abrasion is we have to consider the different types of tools, obviously, that we have on the cutter head. So we have the disc cutters to start with. I think more or less everybody's familiar with this type of tools. And disc cutters are not so much a tool to excavate soils. However, they are installed in many projects excavated in soils. So that's why we're also presenting the disc cutters here, although they're actually hard rock tools. They play an important role in soils, especially also to maintain or to assure a proper periphery of the excavation, to assure that we have enough profile of excavation, and that the TBM is always going to have a gap to push through into the ground and not to get jammed. So this is, in this sense, it's one of the main aspects for the disc cutters in the periphery area to assure the excavation profile. And of course, these discs, they obviously suffer from wear. We can see a picture on the bottom left. And actually, one of the reasons that they suffer wear so much and that they become a crucial tool to decide when we have to enter the excavation chamber to do an intervention is because they are located in the outermost part of the cutter head, often with where we have the highest speed, so higher wear rates, as we will see later on. And also we have to enter more often to change them, or we have to change them more often than other tools, because we don't want to risk the TBM getting jammed. Then we have properly actually soft soil tools, which are the scrapers and the buckets. Okay, and these, of course, you can see I've presented this slide in previous presentations. We have the scraper that literally scrapes the soil on the tunnel face. We exert a force from the cutter head in the direction of advance, and the cutter head is turning. So we actually have a contact force which is penetrating into the soil, the tool, and we also have the tangential force produced by the rotation of the cutter head that scrapes and loosens the ground. Obviously, with this friction, we get tool wear on the scrapers. Yeah, and also the same situation we have on the buckets installed on the cutter head. They also suffer from wear due to abrasion, due to friction. That's why here's a very schematic picture, and you can see it on these photos. We have wear protection bits or sometimes plates on the tools to protect the tools. Sorry. And they are very wear resistant, but after a given, let's say, travel path on the tunnel face of several hundreds of thousands of kilometers, they eventually wear out. Even the wear protection bits, they wear out, and we finally get wear of the steel structure of the tools, which is then critical. Here, before this occurs, we would actually have to change the tools. And then we have another type of tools, which is also used in soft soils instead of the disc cutters, although from our experience, still the disc cutters are used in soils more than these tools that are the rippers. Yeah, and rippers, I think they are a very useful tool to excavate in soil, and they obviously also suffer from wear, and this is something we also have to analyze. And there's, however, abrasion is one aspect. Yeah, then there's clogging, for instance. Yeah, clogging of the cutter head also governs the wear that tools are going to suffer. Yeah, we have the clogging. You can see on the left-hand side a picture of a cutter head with this is actually a ripper protruding out of the cutter head, and you can see the cutter head is covered in clay, in a muck, in a sticky muck, and this, of course, hinders the flow of the material from the tunnel face into the openings of the cutter head and into excavation chamber, and this can increase the secondary wear. I didn't mention it before, but the wear produced directly by the scraping or the cutting process by friction is what we generally call the primary wear, and this would be increasing the secondary wear. Besides this, clogging also produces a blockage of discs, which produces a higher wear of the disc because the disc starts to flatten. You can see that in certain pictures later. It flattens, it gets blocked, and then that starts to wear very easily because it's not turning, it's not working properly. And then we also have the blockage of the cutter head openings, which sometimes they just block the cutter head. You can see some pictures here of blocked openings on the cutter head. And then here is also another criteria for entering into the excavation chamber. We don't only have to enter sometimes to change tools for wear, but to clean the excavation chamber and the openings when we have a lot of clogging. So this is also an aspect to take into account when we're planning interventions. And then there's other factors that obviously produce wear and tear or damage on the tools, and they would also require for intervention, which is when we have impact loads, for instance. Yeah, impact loads that produce breakages or chipping of tools, and then it's also obviously necessary to enter the chamber in these situations. Yeah, and actually when we have severe damages on the tools and they're not working properly anymore, then it's actually imperative to do an urgent intervention before further damaging the cutter head. This can happen in very few rings in shield tunneling, especially, let's say, in EPB tunneling. It can happen in very few rings that we have a large damage if we don't do an intervention in time. And in this case, we have worst case scenario where sometimes it's just have unstable conditions. It's not possible to enter the chamber anymore, and we have to access the cutter head from a shaft, from the surface, and repair the cutter head. That would be a worst case situation. So there's another several aspects obviously related also to the cutter head design. Excavating exactly the same tunnel in the same geology, we will have a different situation regarding tool wear, tool consumption, and interventions, depending on the cutter head design. This we've seen in many projects. So one of the first aspects in cutter head design is the selection of the tools. Obviously, we have the soft soil tools, as I mentioned before. The scrapers, there's not only one type of scraper. There's different widths and different shapes of scrapers. And selecting the right type of scraper for a clay geology or for a more sandy or gravelly geology is crucial. Then, obviously, the disc cutters. Yeah, the disc cutters, as I mentioned, they're actually rock tools, but we have them in soils. We also sometimes have to have them because sometimes we have soils with rock, mixed phase conditions, or sometimes we have boulders inside the soil. So then the only way of handling these rocky parts of the tunnel face is with disc cutters. And this we can handle with different sizes also of disc cutters. 17-inch, 19-inch would be a usual diameter. in the more or less the metro tunnels or the bigger road tunnels. And the deciding what type of cutter depends not only on the strength of the rock or blocks that I'm going to encounter, but also on the capacity. The bigger the disc cutters, a less number of disc cutters I can install. It depends on the size of the cutter head. If I install bigger disc cutters, we also will have a lower opening degree of the cutter head. So there's many aspects. It's not always better to have many disc cutters. Sometimes we have to have less because it's other aspects that we have to take into account. And then we also have the rippers. And this is a discussion. Actually, we have sometimes in many projects whether it's preferable to use rippers instead of discs. And here we have a nice study from the doctoral thesis of Köppel in Munich, where he's presenting this graph showing that on cutter heads on the left-hand side, sands and gravels, on the left-hand side, the two first bars, they're showing the travel path of the scrapers in projects with installed with disc cutters, okay, where the disc cutters are protruding over the scrapers, and we have, let's say, lower travel path times of the tools, or let's say lower lifetimes of the tools compared to a situation with rippers on the cutter head. Yeah, the rippers are very robust tools, much robuster than disc cutters. They can withhold longer periods of time of working, and you can see even in this case, in this study, it's showing that the use of rippers instead of disc cutters increased the tool lifetime practically from the scrapers 3.5 times almost. So this is always a factor to take into account, the use of rippers, according to our experience. Then regarding the cutter head design, we have the opening degree of the cutter head, and this is also obviously very important. Yeah, we would normally like to have large opening degrees like the one on the right-hand side. 40% is pretty much close to the maximum we can usually have in soils. Obviously more openings means the material will flow easier towards the back of the cutter head through the openings into the excavation chamber, and that's what we always want. We don't want the material to be moving in front of the cutter head very long, producing secondary wear. And obviously this depends if I can do, let's say, a larger opening degree like the one on the right, which is obviously less robust than the left-hand side one. This depends on what loads this cutter head has to go through. So actually, sometimes we need a very robust cutter head structure. That means a more closed cutter head structure, because we have to cross mixed phase conditions with hard rock. So we need a more robust cutter head, or also with boulders. And it also depends on the technology. EPB's technologies generally require a more robust cutter head than slurry shields. Not necessarily always, as I will explain now. And also it depends, the opening degree depends on the required quantity of tools. So if I'm going to hit hard boulders or mixed phase conditions with hard rock, I need a lower spacing of the disc cutters. That means the disc cutters have to be closer together, and I need more of them. So then obviously I have to work with a more closed structure of the cutter head. An example showing you here on the left-hand side, it's actually a cutter head that was for an EPB shield. Sorry, for a slurry shield on the left-hand side, and a cutter head for an EPB shield on the right-hand side. So in this case, it's an exception. As I mentioned, there's no general rule. In this case, we have a lighter cutter head design for an EPB than for a slurry on the left-hand side. And that has to do with that the left-hand side cutter head was for a very complex geology in Singapore with a lot of mixed phase conditions, with soil and soil at the top, granite at the bottom, and a lot of boulders in the transition zones. So it had to be designed as a very massive structure and designed with a lot of disc cutters to handle very resistant rock. And on the other hand, we have EPBs on the right-hand side, an EPB shield, which is excavated purely in the same geology, in a clayey geology, very, very homogeneous. So here we don't have any especially high loads, and we don't have also especially strong ground. So it's possible then to do the structure of the cutter head lighter. And obviously, the situation on the right-hand side will be more favorable for to minimize wear, etc. But it's not always possible to do it that way. And also the cutter head center. I will present several slides in this presentation regarding the cutter head center. It's one also of the, together with the gorge area, the periphery of the cutter head, where we have a lot of wear. The center is also part of the cutter head where we suffer a lot of wear, because precisely the cutter head rotation speed, or the rotations, the linear velocity in the center is very low compared to outside. So the material in the center is practically can't move anywhere. And besides, sometimes we have to install tools also to excavate the material right in the center, which makes us have the cutter head very close with very low opening ratios. However, there are optimum designs, more optimum designs than others. You can see this comparison here. These are actually two reference projects with very similar diameters. And we can see on the left-hand side a cutter head design, which is much more closed, okay? We're comparing the area in the center, which is completely closed. It's much higher in the left-hand side, almost 3 square meters compared to the 1 square meter on the right-hand side. And it's not only the right in the center, also around the center, that's a red circle there. We have all these angles between the spokes of the cutter head, which are normally going to get blocked also. And these areas also in this cutter head on the left-hand side is also very big, much larger than the area on the right-hand side. So all these are details which have an effect on disc cutter wear or tool wear. And here we have a photo of a cutter head in the center of the cutter head. And you can see how there's a lot of material clogged and stuck there, because it's obviously a point, as I mentioned, where there's hardly any linear rotation velocity of the cutter head. The material stays there, doesn't move towards the outer openings. And then also the discs, in this case, you can see the discs marked with the white arrows. They clog, they get blocked, and they flatten. You can actually recognize how they're flattening. And this is what I commented before. Discs that are blocked and flattening can then finally result in the wear of the whole disc, of the whole cutter, and then start wear on the cutter head structure, on the steel of the cutter head structure, which is also then very critical. Then there's other design aspects. I'm pointing out all these because these are actually all parameters that we can more or less actively design, and they have a very relevant influence on the cutter head. So it's a level of protrusion of the disc cutters over the cutter head and of the scrapers or the rippers. Okay, and generally, depending on the geology we have, if we know we're going to hit cobbles and boulders in the soil, then we need to plan a height of protrusion of the tools that's high enough to allow for the flow and movement of the material easily in front of the cutter head, instead of a very, if we had a very closed or a very small protrusion, then it's more prone, the cutter head structure and also the tools and the scrapers, to suffer from impact loads and wear. And there's other aspects, like when the cutter head is large enough, we can install also hub protection wedges that protect. Here would be the position, the housing of the disc cutter. And here we can actually, with these wedges, welded wedges, the disc cutter hubs, which is actually the body of the disc cutter, is more protected against impact loads or against even secondary wear. So obviously, this is only possible when we have enough space on the cutter head to start installing all these wedges. And then scrapers. Yeah, scrapers, these are tools that sometimes, especially if we start having more gravels and cobbles and boulders, they suffer a lot. And here the design of the scraper is very important. There's a very basic thing, but it's sometimes we miss it in some designs, which is the back protection of the scrapers. Yeah, the scrapers, if they don't have, you can see it on the photo here, this is what we call, this is the scraper protruding out from the cutter head, and this is the back protection. If we don't have a back protection, yeah, then first of all, when the cutter head is rotating in the direction opposite to the scraping direction of the scrapers, then material accumulates on the back of the scraper, and also then particles like gravels or cobbles or pebbles, cobbles or stones can actually also damage the scrapers. Yeah? While the back protection protects the scrapers when they're not working in the scraping direction. Then there's another set of governing factors, and that is actually the actual TBM operation. And here we should make first a very important difference between EPB shield technology and slurry shield technology. EPB shield technology, we are operating with high density in the excavation chamber. It's muck, so this is generally tends to have higher tool wear rates because we have a dense muck that we're excavating. On the other hand, the EPB shield technology allows to carry out foam conditioning, and actually the foam conditioning EPB shield technology is a key aspect to minimize tool wear. And then the slurry shield technology, where we are actually operating with slurry, with a slurry suspension, actually liquid consistency in the excavation chamber. And that, from that point of view, we tend to have lower tool wear rates than in EPB shield technology. On the other hand, contrary to the EPB shield technology, we have no possibility to actively reduce abrasion. Now, regarding the TBM operation, it's the impact of the travel path. Yeah. So the travel path of the tools, that's actually the kilometers, because we're talking in kilometers of path of the tools while they rotate on the cutter head, depends linearly, or the mass loss in this case. This is a study also from the doctoral thesis of Kuppel. The mass loss has a linear correlation with the travel path of the disc cutters on the cutter head. And the travel path, this is something for the same length of tunnel that we can actually control, yeah, with the cutter head revolutions and with the penetration. We can actually operate the TBM in one way that will produce a lower travel path and lower wear on the tools. The same actually happens, same behavior we see with scrapers, an increase of the mass loss linearly with the travel path of the tools. And this is seen on the left-hand side, and on the right-hand side, we can actually see the travel path measured or attained by scrapers in a project or in several projects against a soil abrasivity index. Now, later on, we'll go very briefly through the different abrasion test methods there are. And so, but well, soil abrasivity index, the higher the value, the higher the abrasivity of the soil. And here you can see how with the higher abrasivity, the travel path reduces exponentially, and then it tends to stabilize when in the high abrasivity area, but there is a big influence of the soil abrasivity on the attainable travel path by the scrapers. And again, the rippers, we have these figures for the rippers. which follow also very much the same shape or the same tendency as with the scrapers. So the tool travel length is actually crucial in the wear, obviously. And then the TBM operation. Yeah, we can operate the TBMs and design the cutter heads in one way or the other, which will make the excavation more prone to wear or not. And one parameter that's always correlating very well with wear is the specific energy. This chart I've also shown in a previous webinar. We had, this is an example. This is actually a slurry shield, and you can see on the horizontal axis, it's the ring numbers along the alignment. And the blue area is what we call the specific energy, which is measured in megajoule per cubic meter of excavated ground. And the black bars are showing the interventions that were planned in this project. And in orange, we see the bars of the interventions that had to be done and they were unplanned. And obviously you can see at the very beginning, there were no unplanned interventions. We had specific energies more or less in an acceptable range, 10 to 20 megajoule per cubic meter. But as soon as we started to encounter more difficult ground conditions, the specific energy started to increase, and all these unplanned interventions had to be done. So the TBM operation itself, which we can also, let's say, improve or control in many ways, also has a very big impact on the resulting tool wear, tool consumption, and number of interventions. So now a brief sheet or slide on the abrasion or the measure of the abrasion. Yeah. So from the soils, these are the main tests we normally get from the projects regarding to measure the abrasion of the soil. So we have on one side the equivalent quartz content, where here the percentage of minerals is calculated or is determined in the laboratory in percentage, and then applying the formula here at the top, which is just a percentage of each mineral multiplied by its residual hardness value. Then this gives us the so-called equivalent quartz content. And there are correlations between the equivalent quartz content and tool wear, for instance. From the equivalent quartz content, it's also possible to determine the soil abrasivity index, SAI, which is taking into account the equivalent quartz content, but also the shear resistance of the soils and the B60, so the particle size distribution of the soils. This is a method that is very, very rarely, or this parameter is very, very rarely given in projects. Then the LCPC test is also a wear test, pretty standard, that is used in many projects, and there are also some correlations, but no conclusive correlations between the wear and the LCPC values. The LCPC consists on this engine, and you can see where the number 2 is. There we install this fixed plate with a given measure and weight, and it's then into this little pot. Number 3, we have the soil that we're testing, and then we rotate this plate inside the soil at a given speed for a given time, and the change in weight is measured of the plate. You can see some plate examples at the bottom with different wears. And this gives us a classification for the LCPC. And then we also have the SAT value, which was developed by the Trondheim University in Norway, and they also measure the wear of given steel body while material is, let's say, flowing under it, moving under it. All these tests have their own specifications. They're only valid for certain grain sizes, etc. They have also a lot of limitations, but this is basically what we get from the projects. No much more than this, okay? And there's no direct correlations to date yet between these parameters and toolware, although there are some empirical relationships in the literature. So from here, we have the abrasion. We can measure it in the soil, and then we need to plan how many tools we will need in a project. Yeah, and this is then we need to know the wear rate, and the wear rate is what we measure. You can see in this table in millimeters per kilometer. So that's millimeters of tool wear, millimeters that we use, that we lose of the tool by wear per kilometer of travel path. Okay, so here we have, this is just an example of values, but what I would like to highlight here, obviously the wear rate depends on the geology we're excavating. In this case, we have a soil, then some mixed phase or some rock conditions, obviously all with different wear rates, and obviously the position on the cutter head of these tools plays also a role in the wear rate. We have lower, we have higher wear rates in the gauge area, in the periphery, because that's where the tools are rotating faster. They have higher velocity, and this produces more wear also. On the tunnel face, on the front, not too close to the center, we have generally the lowest wear rates. And in the center, you can see here, we have very high wear rates, and that's related to the aspect I was explaining before. So all this has to be taken into account when estimating the tool consumption, and also when estimating how often we will have to enter into the excavation chamber. So that's what we call actually the tool lifetime. Yeah, tool lifetime we measure generally in cubic meters per tool. How many cubic meters can a tool excavate? And this is not related to only to the wear or to the abrasion, as we saw before in the table before, which is millimeters of wear per kilometer. This is the lifetime, depends, for instance, on when do I want to change that tool. Do I want to change it when it's already worn out 10 millimeters, or when it's worn out 20 millimeters? Well, then, for example, in the gauge area, the area marked in yellow here on the turning cutter head, we want to have, as I mentioned before, we want to change the tools earlier because we don't want to risk the shield to get jammed. So then we have a lower acceptable wear on the outer discs, which is normally actually conditioning the need of intervention, the wear on the outer area. And then there's other aspects like the clogging or impact loads that I mentioned before that are not related directly to abrasion, that will also govern the actual tool lifetimes. So here there's an example. This is taken from real data from a project. And here you can see the tool lifetime in cubic meters per tool along the different, these are disc cutters in soils along the, or on the cutter head here. In the center, yeah, or let's say the highest tool lifetime we have on what we call the front, so not the periphery nor the center, so at the front. And then we also have in this case a low lifetime in the outer part of the cutter head, in the gauge area, but precisely for this reason, because it doesn't mean that it necessarily wore out faster. It means that I have to change that tool faster because I don't want to risk the cutter head or the shield getting jammed. So that's why at the top we have very low lifetimes. In the front part of the cutter head, we have high lifetimes, the highest, and in the center we have, let's say, also medium-low cutter tool lifetimes. Okay, so you can see cutter tool lifetimes in cubic meters per tool. This very, very low cutter tool lifetime in the periphery, we can see it here in percentage now. Yeah, so it's more or less this. We're showing the percentage respect to the maximum tool lifetime on the cutter head. The maximum is in the middle of the radius, and the minimum in the gauge area even lower than 10% of the actual capacity of that tool if it's installed in another position. So, and this value here at the top is what is telling us when we have to actually plan the interventions. Yeah, when I reach that lifetime that I don't want to exceed on the outer cutters, that's when I actually have to enter and change those cutters. So that is going to govern my intervention strategy. And here's one of the questions. Now we're jumping into interventions. Yeah? When do we have to intervene? Well, we have all our predictions, as I've been describing before, but based on wear rates and on experience. But there's also the TBM, operational parameters that I mentioned before, like the specific energy. Here you see an example. At the top, you can see that the blue line is the specific energy, which is okay for many rings. And then it starts going up. Yeah, so it means specific energy, it's being harder, it's getting harder to cut or excavate that ground. And if the geology has not changed, it means that I'm having already a remarkable tool wear that is being reflected in the TBM data. Another index parameter that we use a lot is a penetration index, these bars in color lime, where it's also here it was increasing as the specific energy increased, also indicating wear. And there's other parameters like the temperature. The temperature in the excavation chamber also starts to increase when the cutters are not able to cut efficiently enough because they have too much wear. Then a lot of energy is dissipated, not in cutting or loosening the material, but just in higher friction and generating more temperature. So all these are indicators. However, experience shows that before we can actually see such a clear reflection of this, of the impact of wear on the TBM data, it's generally better to do preventive interventions based on the estimations that we have performed for tool wear rates, for tool lifetime, and obviously later during the construction, we can optimize the spacings of interventions if these are getting, as we get more familiar on the particular wear rates at the particular project. And here we have an example of how different the spacing between interventions can be depending on the geology. This is also a project in Singapore. You can see the surface is marked with a black line. There's the surface at the top. The tunnel you can slightly see here in gray in the middle. And the red line is indicating the top of the bedrock, okay, of granite. And the rest is then weathered soils. And you can see we have sections in full face soil, sections in mixed face, sections in full face rock. And marked in the colors in the bars above, marked in the colors above are the interventions that took place with the identification of the ground conditions. That's why there's different colors. But each bar represents an intervention here. And you can see the average intervention spacing in full face abrasive granite was 7.3 meters. So that means entering the excavation chamber every 7.3 meters for a tool inspection and tool change. In mixed face, this number was even worse, every 4.3 meters. And soils, in the soil stretches, every 50 meters. So you can imagine what a big impact if you don't predict this properly in your planning of the tunnel or by planning of your bid. It has a huge impact in terms of costs and time. So interventions. Then we know we have to enter the chamber and do interventions. Very basically, there's free air interventions or hyperbaric interventions. Yeah? Free air interventions, we're talking about soils in this presentation. Basically, it's only possible in stable phase conditions, so that would be maybe more in clays, and also in dry or with very low permeability, with low water flows. Otherwise, if we have unstable phase conditions, we have to carry out hyperbaric interventions. And hyperbaric interventions are more complex, and as I will briefly present today, they're also require more. They're more costly in time and money, okay, because we have to compress the excavation chamber with air to work safely. And depending on the pressure we have to apply, that will depend on basically on the water column of water pressure that we have to balance. Then we have different type of hyperbaric interventions, regular compressed air from 0 to 4 bar, depending on the regulations. If we're higher than 4 bar, then we have to start working with mixed gases. And if we're higher than 5-6 bar, then saturation diving. And all these situations are technically quite complex to organize and from a safety point of view. So the procedures, as I mentioned, they are complex to do hyperbaric interventions. Here you see how a filter cake looks like on the tunnel face when we need to stabilize the tunnel face. In sands, for example, you can see a cut here in the ground and the filter cake on the face. And here plays a very important role if we have a slurry shield or EPB shield. In slurry shields, it's quite easy to generate a filter cake because we use the slurry suspension anyway as a supporting medium during excavation, and we have the means of feeding, we have the pipelines and everything to feed slurry into the chamber and to extract slurry from the chamber easily with a good phase pressure control. That's not so easy in EPB shields. EPB shields only have the screw conveyor, and when we start to exchange the solid muck by the liquid suspension, generally we have a very high pressure fluctuations. It's more difficult to carry out interventions safely in EPB technology generally if no additional measures are taken. And then within the procedures for hyperbaric interventions, we have obviously all the aspects related to the compression of the personnel that has to do the works and the deeper decompression times in the manned locks, which also delay these processes a lot, and they make them also more costly. There's a lot of equipment involved and also specialized staff and even medical staff that has to be on site when this takes place. So all these aspects imply time and cost that have a big impact on the project. And then obviously there's a possibility of planning safe havens along the stretch. Yeah, that means you can see it on the left-hand side. We can plan an injected block in the ground, where this is, in this case, it's a short block where we can fit the cutter head in it. And then at least we're working in stable phase conditions. We'll still have water pressure to balance, but we don't have the safety or the stability issue so much, which eases the whole process. We don't have to generate a filter cake, regenerate the filter cake if the intervention is long, etc. And also the other option is to do big safe havens. If this block here is longer than the shield, then it's actually possible to do, if the block is completely watertight, of course, to do practically an open air intervention, or a situation like the one on the right-hand side. This is a mixed phase condition, and we have soil at the top and rock at the bottom. And here, if we inject the soil properly, the soil part with jet grout, you can see the photo here. And if this is done properly, it's actually possible even to seal the soil part. And here, this is the project in Rio Line 4. It was possible to actually enter the chamber in free air conditions to change the tools. So what is the strategy to be taken? It's basically a mixture of all these aspects. First, of course, at the very top, we have the assessment of the geological conditions and the vision of the alignment into homogeneous sections. And then follow the right-hand side here, we have the tool wear rate prediction, depending on the abrasion test results that we have, and also on the experience that we might have from other projects. We can estimate a tool wear rate prediction in millimeters of wear per kilometer. Then also entering the variable what penetrations are possible in this soil. Yeah, if I have a higher penetration, if I can work with a higher penetration, it will be possible to reduce the travel path of the tool, so to reduce the tool lifetime in the end. So entering these variables here, we can determine the tool lifetime, and then we have to check if this estimated tool lifetime matches the tool lifetime that we have maybe in other projects in similar geological conditions with similar TBMs, with similar cutter heads, etc. And from here, then, once you have the tool lifetime, we can start planning the interventions. Yeah, we can plan, okay, we'll have to enter the chamber to change the gauge cutters every 25 meters, for instance. And we'll need so much pressure, we need so much time of interventions, and you can start calculating all the time. So this is the procedure that we generally follow to determine the interventions and the tool consumption. But obviously, I've marked these aspects in red, these rectangles here in red, because certainly the only way of corroborating our predictions is based on reference values, also on literature, on the few correlations that we find in the literature also, but basically from experience to confirm the predictions. So just a very brief concluding remarks. Tool wear is strongly dependent on factors other than abrasion. It's not all about abrasion. TBM type, cutter head design, TBM operation. The tool wear prediction models mostly neglect or underestimate these factors. Yeah, there's actually hardly any models, and it's very difficult to integrate all these variables, which have a big influence, a big impact on the tool wear and tool consumption. And there is still, we don't have enough empirical data because there is no single or widely used abrasion parameter that has allowed to date to have clear correlations and models for the primary wear either. So we don't have that much base information. And finally, the estimation of the intervention spacings, that's the distance, how often I must do interventions, and the design of the interventions also needs to take into account all these aspects. Yeah, and they're basically mainly based on practical experience. So with this, I finalize the presentation.
Thank you, Mark. We have already many questions. I also have a bunch of them. It was really great presentation, extremely useful. I'm sure that we can keep watching this presentation over and over afterwards. So we go to the questions now. Many people saying hello to you. We have first question here from Juliane Oliveira Santos. Mark, in terms of, I can even show the question here. In terms of mixed phase conditions, what do you suggest in terms of operation as well as cutter head design and tools? It's a very relevant question, especially for us here in Brazil, as we have so many mixed phase areas.
Yeah, it's a very relevant question, and it's one of the most difficult questions. Also, we're talking about mixed phase conditions. These are, I think, in every webinar of the three we've done, we've been saying how difficult mixed phase conditions are. So it starts with the selection of the right TBM to handle those conditions before the operation. To select the right TBM, not only the technology but all the specifications. That's a very, very crucial aspect to start properly. Otherwise, it's going to be extremely difficult. And then, operation is based on observing all the parameters. This is something we've always mentioned in these webinars. With digitalization, we can analyze the data in real time and calculate all these other key parameters like the specific energy, the penetration index. And that's very important to monitor those values. As soon as those values start to increase or to change unexpectedly, then you have to immediately be thinking, why is that occurring? Could that be a wear incident? If so, then it's most probably wisely have to do an intervention. Yeah, and cutter head design, it depends extremely on the geology of the soil, the geology of the rock, There is no formula for that. You have to take into account all the variables. So obviously, I mean, mixed phase conditions, you will need hard rock tools on the cutter head. There's no other way of doing it. And as I mentioned, aspects like you need these cutters to protrude as much as possible out from the cutter head to avoid then too many damages on the scrapers that we'll have also installed on the cutter head. And actually, it's a bit all the points that have been presenting in this presentation have to be taken into account when excavating in any geology, but more difficult mixed phase conditions for sure. But there's no clear answer to this question. You know, you have to analyze all these variables, how they are in each project.
I was actually quite surprised with some table you showed with some numbers comparing the wear between soil and rock, and then the mixed phase one. So I was expecting the mixed phase one to be higher than rock, actually, because of the impact load from going from soil to rock.
Well, that,
breakage, no, like because
that was the intervention spacing one, which I think, or
it was the intervention space or
mixed phase, the tool wear rate.
Yes, the tool wear, yeah.
Well, okay, this is the case in Singapore, Daniela, and the rock. The granite in Singapore is just the sound granite, yeah, whether in class 1, 2, it's just so hard and so abrasive that it has this impact. But you're completely right. There could be mixed phase situations where it's the other way around, where the tool wear rates are actually higher, sorry, in the mixed phase conditions. Yes.
Yeah, because I'm not so sure. Like, if you consider when you talk about tool wear, you're also considering the breakage of the tool.
No.
Because sometimes it's not about wear exactly, but it's breakage. No,
for sure. That's what has to do. That's what I was pointing out. The difference between wear rate, which is purely primary wear from abrasion, and tool lifetime. You know, tool lifetime, we have to then take into account, okay, that tool is wearing at a given rate, but then I'm estimating that I'm going to encounter a big boulder every 50 meters, so that I have to consider in the tool lifetime. It might suddenly kill my tool, despite it has a low wear rate. So that's the difference between wear rate and tool lifetime.
Yeah. Next question. Bartolome, I don't know if I know how to say his name. What's the optimal overcut in millimeters, inches, or in relation of cutter head diameter?
Well, this depends again on the geology you have. It depends if you have many curves. For example, if we have a metro tunnel, metro tunnels we normally can have very tight curves as low as 200 meters curve radius, and then there we have to have a larger overcut, and in other projects we can keep it low. Yeah, we normally tend to want lower overcuts, less to excavate, and less possibility of settlement or lower settlement, etc. So again, here it depends on the project. Yeah, and we've had projects, for example, in Sands, Rio, line 4, where we were actually in the sands. The sands were actually starting to be, let's say, act on the shield, and we were noticing we have a lot of friction, and we decided to increase the overcut, the planned overcut. We increased it in 10 millimeters. Yeah, you can install some wedges on the outer tools to make the overcut larger. So we increased overcut 10 millimeters, 1 centimeter, and it helped a lot. It was impressive. It changed completely. So I don't know. We're talking in the range of some centimeters. Yeah, the overcut, like 2 centimeters or so approximately. But as I said, this depends on several aspects for each project.
So next question is from Eloy. Can you explain that slurry test you showed on your slides? How does it work? I'm also curious about that.
That's the HARP ball test, it's called. And it's actually to measure the yield strength of the slurry. Okay, and now I don't remember exactly the theory exactly behind it, but you have all these little balls hanging from the strings. I suppose you saw that, and you make them sort of go into the liquid, and you check which is the first ball that is completely floating and not submerged or not partly submerged in the slurry, and through all the formulas and all the tension, and depending on the curvature of each little ball, then that gives you a correlation which is a ball that did not enter. It gives you the yield strength of that slurry. So it's one of the ways of measuring yield strength of slurry suspensions.
For the mix shoot. Okay. Next one. Um, we have many international guests. I'm very happy about that. Do you think to apply artificial intelligence models instead of empirical theoretical models? That's a nice question.
For sure. I mean, if there is a way of predicting this in some way, it is only possible through fuzzy logic or neural networks or artificial intelligence. There's no doubt. But it's got to be an intelligent artificial intelligence that really knows about tunneling and knows what parameters actually have an influence. And the problem is not all of these parameters we can measure. Yeah, or we can, like always having tunneling. Yeah, to start the ground, the abrasion we can't measure continuously either, and that plays a role. And for sure, no, I mean, if there is a way, it's only through artificial intelligence. I'm pretty sure.
Yeah. I also have an idea that perhaps the shape of the grains could have some influence as well.
Oh yes. There's this some studies focus on this aspect,
Yeah.
on the if it's more angular or if it's rounded. That there's no, I mean, that's a fact that has an influence on the wear rate.
Yeah, still you do not get this information in the GBR, for example.
No, exactly.
Because I tried to do a study and then it was really hard. I had to assume that this was rounded or this was more angular.
Yes.
And so I come again with the same point that we need to push a bit into what we are bringing to our GBR when
Very
we are
much.
doing mechanized tunneling.
That's also a conclusion we're reaching in each webinar, I think.
Yes, I think it's the same conclusion. Yeah. So we are working on that. Next one. So Rob, thanks Rob for telling me that my audio was working in the beginning. Thanks a lot. Thanks for the presentation. What's your opinion on tools monitoring devices? That's great. I was going to ask that as well.
Yeah. Well, I mean, I know these things developed quite much, and I personally don't have much experience with them. Okay, but from what I've heard, they are getting better. Yeah, they are getting better, but of course they imply a cost because tools still wear. You know,
Yeah.
you're just measuring it, and you have to throw that tool away or replace it, and it has a cost. So it's something I think it's not so widely implemented. But for sure, it's one of the ways of, at least, let's say, it's not going to avoid or minimize tool wear, but it's going to avoid severe damage. Yeah, it's going to avoid situations where we have underestimated the wear of the tools and we realize far too late when we have to do a lot of repairs and changes on the curve. So I think it's a very important tool. Yeah, for sure. That should be.
From my understanding, from my time in R&D at Herringknecht, so the DCRM, the disc cutter rotation monitoring and the load monitoring, they help you to avoid to reach certain level of wear that you cannot refurbish the ring, the disc cutter. No, you have to throw away because it reaches the core, and then that's costly, basically, because you have to you cannot repair that anymore.
Exactly. No, and I mean, most cutter heads are equipped with punctual 4 or 5 points on the cutter head that they will give you signal if wear has reached that point. But it's very localized, it could happen, wear could be all around the cutter head except on that point, and it wouldn't tell you the information. So obviously, the optimal situation would be that all the tools are equipped with something like this, for instance, that to really be aware. But still, I think this is a field that will help to avoid excessive wear or damages. Exactly.
Yeah. I have some questions, so now you're stuck with me. How do you do, for example, the change? What's the scheme of changing the disc cutter? So you do an intervention and you see that the disc cutter in the gauge area has lots of wear. Can you use this disc cutter in the center, for example? Just change it.
Exactly. Well, that's the more or less the strategy or the management of the tools on the job site, and this is one of the typical practices. Because you wear the discs on the disc cutter, let's say 10 millimeter on the gauge area, 10 millimeters, but still you could go up to 20, 25 millimeters to actually use a disc. And normally the common practice is to install those cutters of the periphery on the front part of the cutter head to maximize its lifetime. So actually the lifetime of the tool is there, and we're maximizing it for sure, but still we've had to enter early enough to change the disc in the gauge area, although this disc still has some lifetime in front of it. But so this aspect is something that I was pointing out in the presentation, is determining actually the intervention spacing very much.
Yes. And then what about the checking the wear conditions? No, because from what I know, it's manually done. Do you foresee a way that we can optimize that with some sensors, perhaps, that when there is an intervention and somebody goes there to check, that he doesn't need to go with the measurement there and rule and check one by one?
Yeah, I never thought about that actually. It's very time consuming for sure.
That's what I'm thinking about.
It's normally, and it's not only checking that, often they also check if the discs, for example, are still rotating freely to avoid the blockage of discs. Yeah, well, there's a lot of manual work involved there, and extremely time consuming in the geologies where the soils are very abrasive, like the example I was showing there also of mixed phase in Singapore, where you have to enter the chamber so often. Saving hours of intervention would save a lot of money, and also the less hours people are working in these hyperbaric conditions, the safer it is. These are not. It's also all risky operations, so everything that shortens these working times in risky conditions is always good. Yeah, but yeah, I guess the only way would be to install sensors on the discs that automatically tell us on the wear that it's. As I mentioned, this is also a lot of high cost. And yeah.
Sensors are some kind of laser tool that could at least get this condition.
Scan the cutter head quickly. Yeah. Mm-hmm.
Because this exists already in the industry, just needed to be crossed over to tunneling, probably.
Yeah. Then we have other aspects in tunneling. Tunneling is normally quite a dirty job. And then the disc cutters first, normally before checking them, you have to clean them.
So no matter what, you have to clean them. But what makes easier is that you could scan, and this data could go straight to your PLC system or
that would be very nice.
Your data system. That makes easier, in terms of database and taking the solutions afterwards. Okay, I have one last question. What about EPB tunneling in rock, pure rock?
Mm-hmm.
It's a huge wear. how do you think we could solve that? Okay, we have conditioning.
Exactly. You have the condition. We have a lot of projects of EPB in rock.
Yeah,
And I mean, if you have an EPB in rock, it means that you need it sometime. I mean, if it's a pure rock with no water, with no instabilities, then obviously you will not use an EPB. You will use a rock TBM, extracted material from the Featherhead Center. But if you need an EPB in rock, we've followed projects like even crossing sections in basalt, in very hard basalt in Panama, Metro Line 1, for example. Very nice project, EPB full in rock. And then you have to play. Okay, the key aspect there is obviously the design of the cutter head. That's crucial. Or even the project of Toluca, Mexico Toluca, EPB in
yeah,
rock, which we presented in the ITA awards. The key aspect there is the TBM design for sure. The cutter head design is crucial, maybe more crucial than in other type of grounds. And then the operation, yeah, and you have to avoid overloads of the tools. And generally, then we start talking about the operation modes of the EPB shield technology. We try not to work necessarily with a full chamber of heavy abrasive muck. We try to work with a partly filled chamber and conditioning a lot with foam. So there is a lot of experience, and the key there is I think very much cut head design and operation. Yes.
and the screw conveyor. No, we didn't talk about the screw conveyor wear, but it does happen in some projects and then quite high wear. Because
It
the worst
does,
can happen is that you have to remove your screw conveyor to and
which is
replace it.
which is not nice. It's a very
No.
tough job. I mean, the screw conveyors are very protected against wear, and but obviously in long tunnels and in abrasive conditions, the screws have to be checked and have to be changed. And there's even projects where they have a spare screw conveyor at site for the case they have to change it, because ordering a new screw conveyor obviously takes a long time. So
Yes.
projects
Yes.
where you foresee this to happen, then sometimes it's wiser to have a spare screw conveyor on site. Yeah.
Yeah. Okay. So many people here saying thanks and saying hello to you.
Mike, hola Mike.
So I think there's nobody sending more questions. I won't keep you busy this time.
No,
And
fine.
so I think thanks a lot, and then I'm already looking forward to the next. What's the next topic?
It's digitalization in tunneling.
Okay, very nice.
Yes. So
Always
no, we're
nice.
looking forward to that one. We're working a lot in that field, and we are planning for Ulrich to hold that presentation. And I think also one of our, let's say, leaders here of all the digitalization that we're doing in the company. So that will be very interesting.
Yes. I would like to give some, just tell what's the next webinars. I'm already showing here. That's great. Yes. So we have in the next one is actually a colleague from Portugal, Gonçalo Gines Vieira, and he's going to talk about the project in Lisbon, the drainage tunnel, the new drainage tunnel.
Mhm.
It's very interesting. And in March, we will have all ladies because March is the Women's Month, no, 8th of March. So I'm organizing two webinars. The first one is Antonia Cornaro from Switzerland talking about future of tunneling. And then 25th of March, we have a very nice roundtable with a bunch of Brazilian tunneler ladies. Then we have, let me find here because I don't. Yes, so we have also in April, we have Ricardo Miranda, safety of tunnels. Still in April, we have Lars Babanderardi and Gustavo Aguiar. And then we have in May talking about emerald gel modeling. And then tomorrow, for those who would like, I'm even going to share here. So we have the tunnelers talk at 5:30 p.m. And the main topic will be this very challenging project, Morro Alto. So that's tomorrow. And also we have to remind you all, we have our 5th CBT for December. Hopefully everybody will be vaccinated by then. The abstract submission goes until February 7. You can send that in Portuguese, English, Spanish, German, I don't think so, but these 3 should be enough. So please just submit your abstract. If you haven't done so, follow our channel, give like in the video, and stay tuned for the next webinars and also for receiving again Mark and Uri Schmeider. So thank you a lot, Mark.
Thank you very much, and thanks for everybody for listening.
And good night, everybody.
Bye-bye.
Bye.